Yes, sir.
Okay, perfect. Okay, guys. So I hope that you have gone through the lecture which I've uploaded on YouTube as well as on Teams also. Um, that is related to thermodynamic relations. So it's quite mathematical, you can see, but very useful. And I've explained everything in detail in that lecture. So I hope you have gone through that video. If not, you'll feel difficulty today, but then you have to go through it. I'll just do two more illustrations on that concept, what we call as thermodynamic relation. Then we are going to do the last topic, which is equation of state, and then some very good problems on availability. And this way we will close my module. And then on Friday, when you will meet with Professor Gargidas, there will be a short test, 10 minutes or 15 minutes, something like that. Problem will be, a number of problems will be more, so time will not be sufficient, that's for sure. So don't try to attempt everything. Okay, that's the strategy which we have to follow in order to, like, people sometimes just for good grades they want to copy. So just to avoid that, I'm not blaming anyone, but just to avoid that, we will keep the paper lengthy. So don't worry that you won't be able to solve the whole paper. Okay, so let's attempt this problem that prove that mu jet is this. So mu jet is nothing but Joule Thomson coefficient. If you remember, we defined it fundamentally as dou T by dou P at constant H. If you remember the throttling process, if not, refer to that lecture. Okay, where we have plotted T as a function of P at constant H. Okay, constant enthalpy line. I am not going to repeat the experiment. We have discussed it in detail. We have many insights also regarding throttling. So I hope you understand. Great. So see, mu jet is dou T by dou P at constant H. Think here that basically we are trying to correlate HPT. Okay. So one strategy can be that we have three properties, right? H, P, T. We know that I can correlate H with P and T. Okay. So if I can correlate H with P and T, it means I can write f of HPT equal to 0. And if this is true, then using the cyclic relation, okay, which I have derived in the assignment solution, you can check it. We can always write following. Let's say HTP and then HTP. We will follow this cyclic order. So if that is the case, dou H. So we are using cyclic relation. Dou H by dou T at constant P, then dou T by dou P at constant H, and then dou P by dou H at constant P. This is completely from mathematics, true for any such relation where you have this. So basically it tells you that there is only two independent variables. Third one depends on other two. That's why function of these three variables is 0, some functional form. So this we have. Now you can see clearly that we need this, okay, this thing which is present here. So it means I can write dou T by dou P at constant H is equal to, we can write it as dou H by dou T at constant P, 1 minus sign, and this will also go in the denominator, but if I can flip it, and I can put it here at the top. Okay, fine. Now can anyone tell me what is this? Any guess? You have this relation which you want to derive, so there is a hint what it can be. Dou H by dou T at constant P.
CP.
CP, right? Because at constant P, heat given to the system is dH, and we know that definition of CP is dou Q at constant P by dou T, right? And dou Q at constant P is nothing but dou H. Very good. So we can replace dou H by dou T at constant P with CP. So this will be minus 1 dou H by dou P at constant T, and then we have this Cp. Okay, wonderful. Now if you remember, we can express dH in terms of T and P also. Let me express it. And that also I have to see. I don't remember how. Oh yes, we have this diagram now. So you see, I want dou H by dou P at constant T. We have used cyclic relation. What else we haven't used? You remember this diagram, the trick? So S goes to T, P goes to V. For them who are thinking, what is this? You haven't seen it before. It means you haven't gone through the lecture which I have sent you. So that you have to go through. And then if you remember, you can make some poem or something to remember the order H, G, A, U. You want to write DH. Let's write it. DH. DH is connected with S and P. So can anyone want to try? What I should write? DH now equal to? First write the differentials.
PP.
DS and DP. Very good. Then S goes to T. So put T, and P goes to V. Put V. Now arrow is going. See the differentials. Arrow is going from S. So plus sign. And arrow is going from P. So plus sign. Okay. So this relation we have already, apart from cyclic relation. Now from here, if you'll write it, if you'll take the differential with respect to P, because you remember in the last slide we are looking for dou H by dou P at constant T. We are looking for dou H by dou P at constant T. So take the differential with respect to P, differentiate it with respect to P at constant T. So dou H by dou P at constant T is equal to T, and then we have here dou S by dou T at constant, sorry, dou S by dou T at constant, dou S by dou P at constant T, dou S by dou P at constant T plus anyone? So there is a minus, no, I haven't missed
Plus
anything.
V.
Yes. Plus V. Okay, fine, perfect. Now we don't want S and P and T all this. Okay. So how we can realize this dou S by dou P at constant T with VTP, let's say. I want pressure, volume, temperature. What we should use? Maxwell relation. How we will go? Yeah. So you can try, start from S through P
H
till T, right? So from Maxwell relation, Maxwell, dou S by dou P at constant T is equal to, go one step ahead, come back till P, dou V by dou T at constant P. Now what about signs? So here in the numerator we have S. S arrow is going away, so plus sign. V on the top, arrow is coming, so minus. Okay. So we can replace dou S by dou P at constant T with this dou V by dou T at constant P. So let's do that. We have dou H by dou P at constant T is equal to V, we can put ahead, and then this minus is there, so minus T is there, dou V by dou T at constant P. Perfect. Now we are quite closer to the relation which you want to prove, but before that, what we can do here, if you see, okay, let me see what else we have. Yeah, fine. What you can do that, if you remember the definition of beta, which is expansion coefficient, beta is nothing but fractional volume, means change in volume, dou V by V, and with respect to temperature, how it is expanding, so dou T at constant P. Okay. So if you will take V common from this, so what we are going to do, we are going to take V common. So dou H by dou P at constant P is equal to V common 1 minus, we have T of course here, dou V by dou T at constant P, and then 1 V here, and we know that this term is beta. So basically what we will get, dou H by dou P at constant T is nothing but specific volume 1 minus T beta. Let's encircle it, and now we'll put it in our main relation. So you can see here, we want this, which is equal to this. So dou T by dou P at constant h, that is our requirement, is equal to minus of dou H by dou, I guess, dou P at constant T divided by Cp, and we just got, sorry, where it is, where is that slide? Oh, here we got dou H constant T, V common 1 minus T beta. Okay. So V common 1 minus T beta, and minus sign is there, so it will be V common T beta minus 1, and then here we have Cp. That's what we wanted to derive. There's nothing but mu T. Okay. So that's it. We have used here cyclic relation also, Maxwell relation also. Then we expressed DH also in terms of ds and dp. So we have used everything in this problem. Great. Perfect. Next problem. Next problem is very important, and here you can say it's the beginning of the second module, which is something called this called phase equilibrium. Phase equilibrium. So from now here onwards, we will dive into phase change or phase equilibrium. We will talk about phase equilibrium. First, we'll do single phase system like water. It can go to liquid, vapor, solid, and then we will enter into multi-component system. The moment you enter multi-component system, chemical potential will come in picture. So that is the part of second module. The main focus will be there, and of course, focus will also that how real gases deviate from actual gases. I mean the ideal gas behavior. Okay. Remember the relation like the you have derived. Let's say we have just seen. So, for example, you see this relation. You know that entropy is not measurable, but you can always express dH is like this. You know, dou H by dou P at constant T or something like this. For example, you have derived dou H by dou P at constant T is V into 1 minus T beta. Let's write it. What you have derived? Dou H by dou P at constant T is V 1 minus T beta. So one can ask you, he will give you some equation of state, let's say van der Waal. So you have to calculate the expression for beta, and then he can ask you that, let's say, entropy at a given point is known, and if you conduct that process at constant temperature, okay, with pressure variation, what will be the enthalpy at state 2? So basically these relations we use to calculate properties, thermodynamic properties. Okay. In terms of what is measurable, like you can measure beta, you can measure T, you can measure specific volume. You have to keep in mind that this relation will only work if your pressure is, if your temperature is constant. Okay. Once you know H2, H1, then that DH is valid for any kind of path. But in order to calculate that, you have to follow. If you're going to use this formula, you have to keep this criteria in mind. And of course, at a given point, you have to know the property because it tells you the change, not the absolute value. Okay. So basically, if somebody wants, he has to go like, if someone wants, he can approximate it, you know, by, if possible, not always, you at constant T is equal to V1 minus T beta. But then again, question arises, beta may depend on T. So this may not be a good approximation. So depending on problem, whatever data given, you can play with this. Okay. Can anyone tell me what is beta for ideal gas? Just check. I'll write the relation if you don't remember. Fractional change in volume with respect to temperature at constant P. Now check. What is beta for ideal gas?
NR by PV.
What?
NR by PV.
No, N, it's everything is specific, na? Just say PV equal to RT.
1 by T.
1 by T, correct. 1 by T. Oh no, 1 by T it cannot, it should be T, na? Just check. Oh no, dimension wise it should be 1 by T, I think.
1 by RT.
R is also coming? Is
1
it?
by T.
R will come. It depends on what unit we are. So PV equal to RT, right? So dou V by dou T at constant P. So P is a constant, is equal to R, right? And then you have to divide it by V both sides. So divide it by V. So basically, and then P will go that side. So this is our beta, right? And this you can write PV equal to RT. So 1 by T. Yes, RR will get cancelled. Very 1 by T. Okay, fine. Okay, great. Now let's go to what I said. This very important step to phase equilibrium. We'll do it quickly, and then we'll go to equation of state, which will take maximum half an hour. Quite straightforward, just informative, and then some problems on availability, and that's all. Okay, today we are going to learn in this, the first thing which is we are going to learn is called very famous equation. It's called Clapeyron equation. Clapeyron equation. In many books it is Clausius-Clapeyron. That's fine. Clapeyron equation. Okay. It's valid for phase change. When phase is changing, means you have equilibrium mixture. Equilibrium mixture. And what it's going to tell you, let me tell you before we go ahead. Basically, what we are going to prove is as follows: that dou P by dou T at saturation line means this is P sat, this is T sat. Okay, you can write dou P sat by dou T sat. That is also fine. You can write dou P sat by dou T sat. That is also fine. Is equal to delta H, where I will tell you what is delta H. Delta is associated with phase change. Okay, means when liquid is going to vapor, what is the delta H? So you can write it Fg. Okay, fluid, liquid going to vapor, into T into delta V associated with phase change, F into G. So basically it's correlate saturation pressure with saturation temperature. So you can remember the steam table which we have seen. One can verify that whether this Clapeyron equation works for their that, because you know, for every pressure you know a T sat, or other way also. For every temperature you know P sat, P saturation. So you can check whether the data given in steam table, how much well this model, Clapeyron model, can predict that data which is given in steam table. Because steam table we have prepared from experiments where this is. So let's do that, how we will reach to this equation. So I'm just repeating, we are trying to correlate how P saturation should vary with T saturation or otherwise. Means if P is given, what will be the T sat for that point? Assuming that you have an equilibrium mixture. So the moment you say equilibrium mixture, it's better we draw this phase diagram. Let's say P and T. Okay. You can check if you don't remember. This is, there are 3 lines. Vapor, liquid, solid. Okay, and this is called triple point. You know it very well for water. Okay, in general this is true for anything. So triple point where all these 3 phases can coexist. Now let's say, since you are saying that you want to know that how this P sat vary with T sat, you have to move along phase line. Let's say we are talking about liquid to vapor. So when you will move from 1 to 2 along this phase line, okay, then how P saturation is going with, because this is saturation line. So whatever you will read on this curve, that is related to saturation. Okay. If you don't remember saturation, you remember this diagram, P V diagram. This is saturation line, liquid vapor. This is, here we have saturated vapor, and this is saturated liquid, and in between we have mixture. Same thing. I have drawn PT diagram. Okay. So we want to know if we go from 1 to, if you vary the T sat, T temperature, how P sat is going to vary. Okay, provided we have this equilibrium mixture, liquid vapor mixture. Okay. Now let's say from liquid side we say 1 to 2, and from vapor side let's say it 1 to 2 dash. We know both are same, but just because we are moving on the same line, eventually we'll remove this 1 dash. This will be same, 2 dash, 2 equal to 2 dash. Okay, fine. Now can anyone tell me quickly that since we are talking about phase change, we know that temperature and pressure is going to be okay. Do this way. If I am talking about 1 and 1 dash, listen carefully. I am talking about 1 to 1 dash. What is 1 to 1 dash? Phase change at a given temperature. There will be some temperature here, let's say T1, and pressure will be some P1. Both are sat, of course. This is T1 sat, this is P1 sat. Okay. So when you have mixture at 1 or 1 dash, you have both liquid vapor mixture, right? Liquid plus vapor. When this 1 to 1 dash is taking place, what is constant? Temperature and pressure. I'm not going to 1 to 2. I'm saying 1 to 1 dash. They are at the same point on saturation line, because if you want to see on PV diagram, probably you will appreciate it more. Basically, you are, let's say, somewhere, so draw isotherm, okay? So let's say this temperature is this one. This is isothermal T1 temperature. Okay. So maybe you are somewhere here, okay? And then you are moving along this line for 1 to 1 dash, let's say. 1, this is 1 dash. Okay. Or let's say this is 1. This is 1, this is 1 dash. Liquid is going to vapor, let's say. So that is here only by 1 point, 1 to 1 dash. Okay. So since temperature and pressure is going to be constant, now can anyone tell me what I can write dg using that diagram? H G A U S T P V. So what we can write dg? S T P V. Yeah. G is related to please.
dt.
So dp dt.
V dp.
And then P goes to V and T goes to S. Arrow is going from P, so that's fine. And arrow is coming. Sorry, so from both arrow is going. Na? S to T. Oh, sorry, towards T arrow is coming. So minus sign. Okay, fine. Minus S dt plus V dt. Fine. Great. Since we have only one component, there is nothing here. Otherwise, you will see in next module there something else will appear here. Chemical potential. Okay, fine. For single phase, it is fine. What will happen when you are going from 1 to 1 dash? Tell me about this equation. dg will be equal to what?
0.
0, because
0.
no change in pressure and temperature. 1 to 1 dash, we are at the same point. Okay. So if dg is 0, we can say g1 equal to g1 dash. That's what I was trying to tell you, that if there is a phase equilibrium, then this gives free energy in liquid phase, and in vapor phase is going to be equal. This is true for one single component system. When you will go to multi-component, you will say chemical potential is equal for all components. Okay. So that I'm not going to reveal here. It will take some time. So Professor Gargi will take you there. So, but for single component, if they are in equilibrium, their free energy gives free energy equal in both phases. Okay. Fine. Now tell me what if I am going from 2 to 2 dash, will it be true? Gt equal to G2 dash?
Yes, sir.
Yes, because that is also phase change. Great. So this we have talked about at point 1 and at point 2. Fine. Now let's go from 1 to 2. Let's follow 1 to 2. Okay, and 1 dash to 2 dash. So let's write what we can write. So if you go from 1 to 2, and remember this relation, dg equals to v dp minus s dt. Okay, dvp VdP minus SdT. Okay. If you go from 1 to 2, means from liquid side, what you can write is as follows. G2 minus G1 is equal to V fluid, let's say, at 2 minus V, sorry, this is VdP SdT, na? Sorry. So how we are going to write it? Just a moment. So if you are going from 1 to 2, of course there is a volume change. I'm just wondering how we will write it. Just a moment. So the confusion is which S and which P we will take while we are going from 1 to 2 in this relation. So we are going for, okay, fine, no problem, I guess. Or is there a problem? Yes, because volume can vary with temperature. How we are going to tackle this? Just give me a moment. So right now it says that no, but this here like for G2 minus G1. No? That's the problem. We are going from 1 to 2, and we have no information about V. So how we can integrate it? That is my doubt. So if I write it, do G should I write it this way? Okay, I think it will work. Fine. Okay. So since we cannot take this VF and SF out of integral, right? Because this will also change. So this I am writing for fluid side 1 to 2. So you can simply see that if we will do this integration from 1 to 2. So you are going through different points from 1 to 2. So this Vf and Sf will be the instantaneous properties. And G2 minus G1 we can write 1 dash to 2 dash, which is same 1 to 2. This will be its Vg. So rather than saying 1 dash 2 dash, simply say 1 to 2. Okay. This time it's Vg because writing for gas side, Vg dp minus Sg dt. Okay. But we know, if you remember, G2 equals to G2 dash and G1 equals to G1 dash. So what we know, G2 minus G1 is equal to G2 dash minus G1 dash. So what we are saying, these two are equal. Okay. If these two are equal, these integrals is also be going to equal. If these integrals are equal with same limit, then integrand should also be equal. Okay. You got the point? Left hand side equal, so right hand side is also equal. It's the integral from same point 1 to 2. So integrand should be equal. So what we are going to write from this is Vf dp minus Sf dt is equal to Vg dp minus Sg dt. Okay. So then what we can write, you can take dp common. Okay. If we take dp common, what we will get is Vf minus Vg. If I put dp this side, and if you take that dt that side, dt, this will be Sf minus Sg. Okay. So basically, since we are moving along the this is not true for any P and T. If this is true for saturation line, we say dou P by dou T. Why dou? Why partial derivative? Because you have to move along saturation line. What we will get is so let's see, there is no mistake here. So it should match with the book. Let's see whether it matches. So dp by dt we are getting fine. So Sf minus Sg by Vf minus Vg. I'm just flipping it. Sg minus Sf, because Sg is greater than Sf and Vg is greater than Vf. That's what we are getting. Okay. Simple. So what we are getting is as follows. Dou P by dou T along saturation line is equal to Sg minus Sf and Vg minus Vf. F is for fluid, G is for vapor, liquid and vapor. Fine. Now, since this is a phase change, okay, so when G is going to F, or let's say F is going to G, both are fine. F is going to G, liquid to vapor. It's a constant temperature and pressure process that we know when we go from 1 to 1 dash and 2 to 2 dash. Okay. Fine. Now, can anyone tell me that if I want to write ds for a phase change, what it will be? As you, we know that phase change is a reversible process. What it will be?
dq by t.
Dou q by which temperature? The instantaneous temperature at the curve. If this is the curve, if you are talking about dou p by dou t at this point, then temperature of this point, Sg of this point, Sf of this point, Vg of this point, Vf of this point, that instantaneous point between 1 and 2. Okay. So dou q by instantaneous temperature at constant pressure, that we know. Of course, temperature is also constant. But what we know that dou q given at constant pressure is equal to? Anyone? dH. You just write so dH by T. So basically what we can write along this saturation line, since everywhere it's a phase change at all points, Sg minus Sf, we can simply write Hg minus Hf by instantaneous temperature. So using this, what we will get is as follows: dou P by dou T at saturation temperature is equal to Hg minus Hf Vg minus Vf 1 by T. So this is the main relation. Okay. So basically, if you want to know that how it is varying, then either you can do a numerical integration starting from one point, because if you'll only take value, let's say if you take any point at this curve, and if you take value of Hg, Hf, Vg, Vf, and T at that point, you will get this slope. But you are not interested in slope only. You are interested in how this pressure, saturation pressure varies with temperature. So then you have to solve it numerically, or you can use this numerical differentiation. Okay. So that I leave on you. Now there are few approximations which makes this equation a bit fancy and easier. What are those approximations? This I am going to write as enthalpy for phase change.
Much greater than
Yes,
VF.
please. Sorry.
Vg is much greater than
Yeah, exactly. Yeah, that is very wonderful. That is there. Okay, so as someone suggested, but that is only true at very low pressure regime. Okay, you can check the PV curve. Okay, so anyway, first write it. Dou P by dou T along saturation line is equal to HFG. So phase change, enthalpy associated with phase change. This is nothing but Hg minus Sf. Remember. Okay, and then we have T and VFG. And as someone suggested, that generally, especially at low pressure, Vg is very greater than Vf. It means Vfg, which is nothing but Vg minus Vf, you can simply write roughly equal to Vg. So HFG, that is not true for HF and Hg by the way, is by Vg T. Since you are talking about low pressure, if we approximate it with ideal gas, if okay, otherwise you can use this formula, no approximation. But if you use this approximation, so if again you approximate with ideal gas, which is only true at low pressure, you know, from assumption of ideal gas, then what you can write Vg, so PV equal to RT, right? So RT by P at that point. Yeah, RT by P at that point. We can approximate Vg with RT by P. So let's do that. In that case, our dou P by dou T sat under those assumption will be enthalpy associated with phase change. Here there is one temperature, and Vg we are replacing with RT by P. So RT by P. Okay. So dou P by P will be equal to HFG R T square dt. You can integrate it P1 to P2. This can be some reference temperature where these two quantities are known, and then you go from T1 to T2. So if you know one point at saturation line, T sat, P sat, you can calculate for other points, and then you can check how much it is true according with the experimental data. Means experimental P and T sat. So if you do that, it's simply ln P2 by P1 is equal to now here again you are assuming HFG is not changing with temperature, otherwise you cannot take it out of integral. So again another assumption, HFG is not is roughly constant while going from 1 to 2. Okay, so then you can take HFG out. So again other assumption. So remember the assumption, don't use this equation blindly which we are going to write. And then if you integrate it, simply R will be here and we'll get 1 by T1 minus 1 by T2. Okay. So this is one famous equation which people use. And it has been seen that even if we have taken so much approximation, in low pressure regime, it works for many gases, many systems, many liquids. Okay. That's all. This is Clausius-Clapeyron equation. What we related, if you are confused, remember this is all talking about saturation. So you can simply say ln P2 sat. This is P1 sat. So P2 sat is saturation pressure at temperature T1, and P1 sat is saturation pressure at, sorry, P2 sat is saturation temperature at T2, and P1 sat is saturation temperature at T1. So if you know one of them, you can calculate other. Means if you know P1 sat at T1 sat, and if you want to know P2 sat at T2, you can calculate it. You have to take some average value of HFG. Okay, great. So this way, this thermodynamic relation chapter is finished. We have done 2 illustrations today on this. And okay, now very small thing which is Gibbs phase rule. Probably this will be helpful to you, and then we will go to this question of state thing. So what is Gibbs phase rule? Okay. Since the moment is a phase rule, we are talking about phase change. So we have equilibrium, phase equilibrium. Okay, we have phases in equilibrium, phase equilibrium. Okay. Let's say rather than a single component system, single phase system, we have C components. What do you mean by C components? You have material 1, let's say A1, A2, A3, A4, such like that. We have these components. Let's say water, ethanol, glycerol. Okay, so components. So I have mixture of these. Let's say these 4. So C stands for component, remember. And P stands for phase. Okay. So let's say if you are along liquid vapor saturation line, not triple point, liquid vapor saturation line. How many phases we have for all components? How many phases? Yes. Anyone? How many phases we have? 2, right? Why 3? Liquid and vapor, right? I'm saying not at triple point.
Okay.
Okay, only 2 phases. Only liquid and vapor are phases existing. So 2 phases for each component. 2 phases for each component. For each C. Fine. Okay. Let's say we're talking about one point at this line. So there will be some T and there will be some P. Is this temperature same for all components? Yes, because we are on saturation on this line. This. Remember, if this is phase equilibria, if you are on equilibrium line, the moment you say equilibria, there are all kind of equilibrium. What are those? Mechanical equilibrium. In thermodynamics, we say it in terms of pressure. So mechanical equilibrium. What else we have? Thermal equilibrium. Between all components. Okay. And what we have is chemical equilibrium. For single phase, just we have seen that G should be equal. Chemical equilibrium. So something like G for multi-component, we have mu. That we will see what is the definition of mu. But right now, let's say there is some quantity which is called mu. Okay, mu I, chemical potential for a given component. Okay. What equations we can write? Let's see. So first thing which I can write is that since we are working on a single temperature, of course we are on this phase line. So temperature for all the components, temperature for all the phases, not components. We can say temperature for all the phases are equal. So remember the Clausius-Clapeyron. We said temperature for a given temp. So T1. So let's say top part will be for phase. So superscript is for phase. Okay. T1, T2, T3. Let's say P phases. PP. How many phases here? We have 2 by the way, right? I'm generalizing it. Let's say we have P phases. So we have this T1, T2, T3, T2. What else we have? Mechanical equilibrium. What we will write? Anyone? P1.
P1 is equal to P.
P3 up to PP. Okay. Great. We have chemical equilibrium also. How we will write? Can anyone say? Yes. T and P is same for all components, so that's not a problem. I said it for phase. What else? Chemical equilibrium should be also there. What we should write? So let's first talk about component 1. Let's talk about component 1. For component, I will use this subscript. Huh? This is for component. For this component, whatever is the chemical potential is phase 1, that should be equal to, for the same component in phase 2, for the same component in phase 3, for the same component in phase 4, and so on, for the same component for the same phase, another component. Okay. Sorry, what I said, this should be P. So for a given component A1, the chemical potential should be equal in all phases. We have just seen it in previous example. So I'm again repeating. For a given component, let's say A1. So when you say for a given component, your subscript is fixed 1, 1, 1, 1. The chemical potential should be equal for all phases. So 1, 2, 3 up to P. So anyone for A2, what will write? Yes. Mu2. So first type mu2 and so on. Mu2. Okay. And 1, 2, 3, and so on. P. All so this we have. Okay. Fine. So this we have. Right. So let's count down the number of equations. How many equations here we have? Can anyone tell? How many? P minus 1. Isn't it? If you have two components, what you write? T1 equal to T2?
Yes, sir.
So as two phases, so one equation, right? So one less. For this also, we have P minus 1. Okay. For this also, P minus 1, and so on, P minus 1. So let's count down the total number of equations. Okay. How many components we have? C. So from chemical potential, how many total equations we will get? Chemical potential equality. How many equations we will get? Anyone? So we have C components. Yes. C plus C into P minus 1. Okay. And then for temperature, we have P minus 1 equations. And for pressure, P minus 1. So how many total? C plus 2, P minus 1. We have this much equations. Number of equation. Here. C plus 2, P minus 1. Okay. Now let's check how many variables we have. Okay. So let's check how many variables we have. So I have to be also careful. So if I write number of variables, then probably we have first of all, temperature is one variable, right? So one variable is temperature. Another variable is pressure. What else we have? Do we write to need volume also? No, because once you write P and T, you know that there is equation of state. So you cannot write V also. So from state variables we have P and T. What else we have? Unknowns. Anyone? Or we are counting not unknowns. No, we are counting total variables. So T and P is fine. What else we have? Mu for each component, isn't it? Mu for a given component for different phases. So if you'll see that we have total, we will have how much? So T and P is fine, and we have two variables. Okay, and then the unknowns which we have for different phases. So if you'll see how many unknowns we have here, mu1, mu2. Let's say we are talking about component 1, A1. How many mu we need to know? Mu1, 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 and so on. And then phase 1, 2, 3, P. So how many we have? Unknowns? P. isn't it? We have P unknowns here, I guess. Yes. So we have P unknowns. So this way, since we have C components, how many unknowns we will have total? Anyone? It's straightforward. Why you are taking time? Oh, I have to call someone name. Anik.
CP.
CP. Simple. Yeah.
CP, CP.
Yeah. CP. But be careful here. And what care we should take here is as follows. Remember that for each component we have one relation. Sorry, we should not say it. For each phase. So if you take one phase, let's say, let's say you take some phase. If you take any phase, all the components are there. You agree? All the components are there. So if you are taking, let's say, ethanol, benzene, toluene. Okay, if we will take vapor phase, all these three components are there. Let's say Y ethanol, Y benzene, and Y toluene in terms of mole fraction. And if we take liquid phase, same thing, XC, XB, XL. Are these things correlated? YE, YB, YL? Mathematically, not through any other thing.
One.
The summation is 1, right? Isn't it?
Yes, sir.
Because it's a mole fraction. So for one phase, using this mole fraction should be unity, summation of mole fractions. How many relation you will get for one phase? 1. Isn't it? What will write? YE plus YB plus YL equals to 1. So how many relation you will get for one phase? One relation. And how many such relations, how many phases we have? P. So you have P equations more, which we forgot. Phase. So if we revisit, so the CP is number of variables, a number of equations this, and we have few more number of equations. What is that? Anyone? How many equations? More. Anyone? Plus? Nidhi? Is it not clear? Not clear?
Yes, sir.
How many? Okay, I think it's not clear. Anik? Sneh?
Sir, can you please explain again?
Okay, what I'm saying is as follows. How many phases we have? Anik? P phases, right?
Yes, sir.
Take any phase. Let's say phase, any phase among these 1, 2, 3. Let's say I take phase 3. In that phase 3, you will have each component present there, isn't it?
Yes, sir.
I say mole fraction is X. So in phase 3, X1, X2, X3, up to XC. You agree? For phase 3rd. Okay. Let's say for this phase 3rd. Right? Mole fractions, you know, isn't it? So what will the summation of these mole fractions?
1.
1. So for one phase, you have one such relation. How many phases you have?
P.
So how many
P.
relations you will have?
P.
P. That's what I'm saying. Simple. Okay. So we have plus P relations more. So we have this much number of equations, and you have this much number of variables. So there is something called degree of freedom, F. Means how many things you can vary, how many things in hand of a user. So that will be, let's write it, C plus 2, P minus 1, plus P minus, oh no, it should be otherwise. Number of equations first come, isn't it? Sorry, number of variables come first. So this is minus, and this is plus. Okay. Let's do it properly. So the numbers of unknowns or variables we have is P into C. And equations we have P minus 1, C plus 2, minus P. Okay? Is it fine?
So number of variables should be CP plus 2. The temperature
Oh, yeah,
and
yeah, yeah.
pressure.
Sorry. Yes. Plus 2. Very good. This we are missing. Yeah, plus 2. Anything else I am missing? We have such P relation, it's there. Total unknowns PC plus 2. The total variables PC plus 2. So if we open it, there is some mistake here, because ultimately it should come F should be equal to degree of freedom, so equal to 2 plus C minus P. Where I am making mistake. This we have total number of equations. Are we getting it? Just check. Or 2 plus PC, and then if you open it, minus PC minus 2P minus PC minus 2P, and then minus plus C plus 2 minus P. What is getting cancelled? PC got cancelled. So there is some problem which we have to check. Okay, I'll check it. I think some mistake I have made. This I'll get back to you. So basically, this is Gibbs phase rule. You can also find the derivation. The way I am doing it, just do it carefully. I have missed something, and there is somewhere there is a mistake while counting the variables and unknowns. So you'll get F. It simply means if you know the variables, if you know the equations, you know how many variables
Sir.
are in hand. Yes.
Sir, I think the variable should be PC plus 2P.
PC plus 2P.
2P.
Why so?
Because for temperature and pressure, P phases are considered.
No. But that we counted in relations, right? We are saying 2P.
Sir,
Huh?
but in variables.
Oh, but yeah, here it will be treated as unknown. Okay. I think you're right.
So 2P we have to take.
2P should be there. Yes. And then it is fine, working, right? Okay. Yeah. That's it. Yes. Thank you. That was a mistake, because when we have treated it as a variable here. You are right. Here. These all are variables, no? Not the moment we are writing these variables, these relations, each individual is a variable. So now let me summarize it so that we will not get confused. Here we will write equations, number of equations, and here we will write variables. Okay. Let's say we take A1, component 1. Let's write down the variables. So since we are fixing the component T1 up to T1, and then for phase I will use other subscript 1, 2 to P. Then same is true for P. For this is component, component, and this weightage. So P1, 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 and phase will go from 1, 2 up to P. Okay. What else we have variable wise? Mu, right? So mu, sorry. mu1 up to mu1. Okay. And then of course 1, 2 up to P. Okay. Anything else? I guess mole fractions, that also variables, no? That also we have to write. So mole fraction, yeah, mole fraction will be for a given phase, not here. So we have to wait. So first of all, let's count this number of variables. How many variables we have here? So here we for a given component, p variables here, p variables here, p variables here. Okay. So total number of variables we have 3p. Total number of variables we have 3p. And then what else we have? For a given phase. So if you take one, oh, that will be, so we have mole fractions also. So if we write for one component, what I can write, let's say x, x1, 1, x1. So component 1 is fixed and we can change phase. So 1, 2, up to p. Okay. So basically 4p variables. 4p variables for one component. And total we have c components. So this will be 4pc. Okay. If I make a mistake again, please you correct. I mean, you do it by your own. I'm just trying again that. So if we count number of equations, then it will be.
Sir, the
Yes.
temperature and pressure will be same for all the component. So we can take two.
No, so that will do count in a number of equations. No? See, either you say temperature and pressure is only two variables, then this you can completely scrap. That's what you're saying, right? It's just a way how you derive this. It's not a big deal. Am I right? That's what you're saying? That why you are writing T11, T12, T1P. Simply say T is one variable for all phases and remove it. So
No,
number
sir,
of
I am
variables.
not saying that that is right, but for each component.
Yes. We are not talking about equations, variables.
Okay, sir.
Okay. So 4pc. And number of equations we have for a given phase, let's say. No, not for a given phase. For all phases, for a given component, T1 dash equal to T2, T1. So it should be equal for all phases. So one will be fixed. So I think I'm wasting time here. That you can. So you work it out, huh? I'll send the recorded lecture. It's simple math, a rigorous task, which you can do. Count number of equations, and then subtract from variables to number of equations. You'll get degree of freedom. Okay, and how it works, why it is useful, I'll tell you. So I'm leaving it this for you. Eventually you should get degree of freedom is equal to 2 plus c minus p. What does it mean? Let's say you are at liquid vapor saturation line. Liquid vapor. Okay, and you are talking about single phase system. Let's say water. Single phase. So 2 plus, how many components we have? Anyone? How many components we have?
1.
1. And how many phases we have?
2.
2. What is degree of freedom? 1. How many variables you know? P, V, and T. Along the saturation line, how many of these variables you can vary? Can we vary 2 variables? Of course, 3 cannot, because we know this is related with equation of state. So can we vary 2 variables then independently on saturation line? What do you think? Can we vary both things independently along saturation line?
No, sir.
No, because if you know temperature, pressure is fixed. So how many how many variables you can vary independently, and other things automatically fixed?
1.
1. And
So 1.
That's what we are getting. Degree of freedom 1. That's what I'm trying to say. So derivation you can see anywhere, but the bottom line is that this gives you that how many variables you can vary. Other things. Let's talk about triple point. F equals to 2 plus C minus P. Single phase. How many components we have? 1.
1.
How many phases? Triple point. All three phases coexist.
3.
3. What is degree of freedom?
0.
0. You can't vary anything. Triple point is fixed. That's all. Okay. Great. With this, take a break. When we'll meet, we'll do, let's say, 20-25 minutes question of state, and then problems of availability, which is very important for you for your future exams. I have some classical problems which will clear everything in terms of problems. Okay, we meet at 12, let's say 14. We have to be a bit faster today. So 12:14. So I'll stop the recording so that we can again start it.